We're starting. Okay. So let's start. Welcome Andre Platzer from Carnegie Mellon, who will speak on differential equation axiomatization.
Thank you. This is joint work with a student of mine, Yang Tang. And the point of today is to tell you something about a recent result where we found out that every arithmetic invariant of a differential equation is provable with this. Well, that's too much of a promise because some invariants are not actually invariants. Then they don't deserve a proof because otherwise we would be violating the Sameness principle, obviously. So restating every arithmetic invariant that is actually also true has a proof in what I'm going to show you. And indeed, sort of the most peculiar part is this use of what I've called differential ghosts. The context in which this shows up is hybrid systems analysis and verification, where in hybrid systems you do have both discrete and continuous dynamical systems intermixed. My favorite example is the Wall-E robot that's moving in a corridor environment like the one out there, and where the robot you need to control in ways to make sure it doesn't bump into obstacles or the wall. And that robot then has a mix of a discrete and continuous dynamics. The continuous dynamics obviously coming from the motion, and the discrete dynamics coming from decision, such as when to accelerate or brake or how to steer. Today we will be zooming in exclusively in the continuous dynamics because yesterday in the talk I already told you how to do the hybrid systems dynamics around it. But the point is you've still got one fixed law for such a system. So there's a whole lot of flexibility, but there's still this principle that you fix a hybrid systems evolution law of the system and then try to predict whether that's safe or not. The classical approach, of course, is that you're given an ODE and you listen to your mathematical reflexes of saying, oh, what do I do with an ODE? I'm going to solve it and then analyze the solution. That's a great approach, except the trouble is that that's undoing the descriptive power of differential equations. The whole point of differential equations is that they're describing even very complicated systems or very complicated solutions in very concise, compact, local ways. So the point is, if you can describe the solution, then of course you can also describe the differential equation. But if you describe the differential equation, then ask for a solution and analyze a solution, and in a certain sense you've undone the whole deal of differential equations. The point is that they're supposed to describe in much easier ways what the system is doing. And so of course, Henri Poincaré's principle from 1881 was the insight that it is probably a better idea to analyze the differential equation itself as opposed to going through the detour of the solution. And that's what we're going to do today, where we will look at the logical foundations of differential equation invariants and identify, let me say that differently. If it's very easy to get all reasoning complete if per question you ask, you're willing to adopt a new reasoning principle or a new axiom. Sure, that's very easy because all you need to do is, if I find a new differential equation and if it's true, I believe this from now on. That's very easy. The hard trick is to identify what's the very small set of reasoning principles that are of course sound and that can then identify everything else that's true in these domains. So that's what we're going to do today, identify a small set of axioms for differential equations. In particular, there's another thing, which is they're also uniform substitution axioms. What that just means is you can take them literally as written. There's no hidden schematic principle in it. A gigantic difference in philosophy and philosophical logic, but also a gigantic difference in practical reasoning principles for these systems. But that's sort of something I would like to suppress today. If you're interested in that, I invite you to look at the Logic and Computer Science paper in which this is described. But the most important point for me today is to try to explain to you, as good as I will manage to do, why on earth something like this should be complete. So everything that's true has a proof in it. So here's the setting, differential element logic, and it'll give you a bit of better sense of how this works is you have a system and you say all behavior of my system is safe, and safety, for example, means that Wally's position is not the obstacle's position, which means at every point that the system can reach, Wally's position is not the obstacle's position, and then you make this more precise by saying always when Wally moves, this is the case, and then you make this even more precise by also writing down a mathematical model for the motion of Wally. So a differential equation, the easiest one that comes to my mind is the double integrator dynamics because it fits on the slide. Some discrete dynamics for the decisions of the system, for example, to accelerate, some program dynamics around it to say I don't always want to break, I want to sometimes accelerate and sometimes break, and then have the discrete dynamics and the continuous dynamic meet, for example, in sequential composition, which just means that first you run the discrete controller, which will or may not change the acceleration, and then you follow the differential equation for some certain unspecified period of time non-deterministically. Now you've had a single shot controller, that's great, but they're not so exciting. More exciting are the ones that you can repeat. And this is now the non-deterministic repetition that says, do a discrete change followed by a continuous evolution, maybe repeat, do a discrete change followed by a continuous evolution, maybe repeat, which describes these kinds of behaviors.
And what is the exact sense of do something, then do something else?
Okay, in fact, I'll show you on 2 slides what the exact semantics is. But of course, what it means intuitively here is that you do this discrete change while you're running a program, basically. After you're done with this change, you follow this differential equation for a certain period of time, and then you get to repeat if you want to. That explains, besides these kinds of break, accelerate, break, some kinds of decisions, which lead to velocity changing and position changing in response to that, according to the differential equation.
What is the otherwise?
The otherwise? Yeah, I elided that from the slide. Really, the else case should be accelerate, as you see in the picture. It just didn't fit on the slide anymore. So here it would be break if need be, and otherwise accelerate just a little bit or something like that. But it's not so important. This is just some examples, just to give you a flavor of what you can write. And then we remember where we came from. We wanted to say that all of the behavior of this particular model of motion is safe, and safety means this. And all of a sudden we have a logical formula that has a precise semantics, I promise. I'm going to show you on 2 slides from now. And we can now ask whether this formula is actually true or not. And of course, this one is not true because you need some assumptions, but logic is good at tracking these. For example, you shouldn't start in a collision state and your brakes should work. And maybe you should start at sufficient distance to the obstacle because otherwise not even braking can save you, and things like that. The point is you can write them all down. Then some of these formulas are true, and these are the systems you should be turning on, and other formulas are false. These are the systems you should stop and not use. It would be very nice if we could tell them apart. Okay, here is the semantics, right? So for these hybrid programs, it's a reachability relation. So a state is just a point in a Euclidean space, or an assignment of real numbers to every variable. And then every program is a state transition table. From this initial state, I can go to that final state and possibly many, right? And then, for example, for this case, you say, the reachability relation induced by a program that has a non-deterministic choice to run alpha or beta, so for example, accelerate or brake, or turn left or turn right, is just the union of the 2 reachability relations for the individual subprograms. And the reachability relation induced by sequential composition, first alpha, then beta, for example, first accelerate, then brake, or first steer left, then steer right, is just the relation composition between the first part and the second part. And for example, the non-deterministic repetition, its reachability relation is simply the reflexive transitive closure, or the union over all nth powers. So for example, that means that alpha star has the same semantics as alpha, or alpha semicolon alpha, or alpha semicolon alpha semicolon alpha, dot, 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 dot. Out of these primitives, you can describe every other computer program as well, just by combining these operators in a bit of a clever way.
Do you require the union to be actually finite or anything?
Yes, this is actually finite. So in particular, the programs you really write down at the end of the day, which will be some finite description, because you only have finite memory on your computer at the end of the day, right? But you can, of course, describe infinite computation out of that. Right? So for example, if you leave off the differential equation, you get one model of Turing machines as a program model. But the point is, of course, that you're adding these differential equations in order to be able to talk about the continuous evolution of the system. And then the reachability relation induced by a differential equation is precisely the set of all pairs, initial state, final state, that are connected by a solution of the differential equation for some duration r about which you don't know anything except it's a real number. And of course, non-negative makes more sense. For the formulas now, the meaning is the set of states in which they happen to be true.
What does the double bracket mean?
That's semantics brackets. This is typical logician's way of saying the meaning of the thing in the brackets is now a mathematical object. So the thing inside the brackets is a syntactic expression, and my computer can represent them. And I'm associating denotational semantics meaning to it by saying the meaning of a hybrid program is a relation between initial and final states. Or the meaning of my formula, which is again a syntactic expression, the meaning of my formula is the set of all states in which it happens to be true. So for example, the meaning of P and Q is the set of all states in which P is true, intersected with the set of all states in which Q is true. Well, what else should it be? More interestingly, and of course quantifiers quantify of the real numbers, but more interestingly is the meaning of the box and diamond modalities. Maybe let's start with the diamond. Intuitively, that means I can run the hybrid program alpha to get to a state where P holds true, and that meaning is simply the relation composition of the reachability relation of alpha composed with the one-point relation or set of all states in which P is true. That means exactly what I spelled out here. It's it's true in the set of all states such that for some successor connected by the program, I have gotten to a state where P holds true. And the box is the dual of that, so it means that it's true in the set of all states such that all successors, by running the hybrid program alpha, satisfy P. So this means there is a way of running alpha to a state where P holds true, and this means all ways of running alpha will take us to states where P holds true. That was fast, I realize. So if you have questions, let me know.
It's just that the way it's written might be unfamiliar to many people.
Yes, this is classical logic, so this is logic 101. Just for this particular differential dynamic logic, so that means all of a sudden, you need to say, wait, what does this mean? Is this okay? Assignment is also very easy, just to point out another one, right? The meaning of an assignment is just that the set of all pairs, such that the new state has been changed. So the old state omega and the new state mu are identical, except at the position of the variable x, where of course the new state should have the value of the expression e in the old state. That's the atomic semantics for assignments. Good. Semantics is good. Now we can write down something syntactic, and it has meaning as a mathematical function. Wonderful. But even better is it, of course, if we can also reason about this, which we would again like to do syntactically in order to make sure that we understand what the reasoning primitives are and can implement it on this little laptop here, for example, so that the computer can help us doing this completely syntactically. Let me maybe start with this one because it's easiest. This axiom or equation of truth is true that says that if I want a system to be safe that has a non-deterministic choice between alpha and beta, then that's equivalent to making sure that all alpha behavior is safe and independently all beta behavior is safe. And if I know that all alpha behavior is safe and all beta behavior is safe, then I know that all behavior of a system that can choose between the two is safe, and vice versa. There is nothing else, right? In particular, with this little principle here, we can rewrite every occurrence of something like this into more formulas that individually talk about subprograms. This is, in other words, perfectly compositional. Just like the semantics is compositional, let's take it a step back. The meaning of every operator is a simple function, for example, union or composition of the meaning of the pieces. That holds true everywhere, down there as well. And because the meaning of every operator is a simple function of the meaning of the pieces, we will be able to exploit that in reasoning to say, oh, but that means our analysis of a bigger system boils down to analysis of subsystems. And that's a good thing because we can only decompose even a terabyte of an input finitely often, because at some point we will be left with just the atoms in it. And for example, if our atom is an assignment, that's very easy to prove it, right? After an assignment, after I put the value e into x, p is true of x, if and only if p is true of the new value e that's going to get in a minute. Easy. Harder, and the topic of today is the question, what do we do with differential equations? Because that's the other atom that we could be left with at the end of the day.
When you say if and only if, do you mean, well, I know this is syntactic, so it's kind of like we write rules, you can rewrite.
Yes, and that's how we're using that at the end of the day. But this is really the equivalence operator. So this means this is true if and only if that is true.
Right. But in the practical sense, does that mean that certain operation like substitute e for x is reversible?
Yes, right. In particular, here, this is where I'm hiding a lot behind this particular axiom here because there's an entire uniform substitution principle going on. And because you need something that makes sure that you also find a way of plugging in E for X in this.
Right.
And that's precisely characterized by...
But E is a particular case.
It's a term, yes,
So
precisely.
if it is true for a particular case, then how can I substitute some general case and say?
Yes, excellent question. And here the trick is Church's uniform substitution. What I'm doing is generalizing Church's uniform substitution principle to differential dynamic logic, then prove that that's sound, and that precisely makes it possible that the intuitive reading we have for that is just, oh, that's fine. You know, whatever E is, I guess I plug E in wherever X used to be. And I guess I need to pay a little bit of attention to make sure that I'm not doing this in places where X already might have a different value, but because it occurs under a quantifier.
So suppose E is 1.
Yes.
And in my old expression, I already have some 1.
Yes.
And now I take X and substitute 1. Now how do you reverse it?
Yes. All of these are excellent questions. The trick in all of those circumstances is uniform substitution because that allows us to have this as an equivalence and then read the P as a predicate symbol of one argument, where on the left-hand side, this predicate symbol gets the variable X as an argument. On the right-hand side, the predicate symbol gets the concrete function symbol E as an argument. And yeah, on that level, it's obvious that the two are equivalent. And then the magic of uniform substitution happens that once you believe in this one syntactic formula, it's not an axiom schema. It doesn't stand for infinitely many things. It's just this one very formula. Uniform substitution can be used to say, oh, but if I believe in this, I should also believe in it if I replace the predicate symbol P with a formula in which some of the argument positions are replaced because they're referred to X, and over here I do that too, and then that precisely characterized under what circumstance such a replacement is actually soundness preserving and when it's not. Excellent question. The same trick everywhere, by the way. I'm just hiding that because it's not exactly the point of today's talk, but good question. There's in fact a Journal of Automated Reasoning article, for example, from 2017, where I spell this out in a lot of detail if you're interested. Okay, this one is also cute, so I'm going to talk about it briefly. This one says, always after first running alpha and then running beta, we're safe, and that's true if and only if it is the case that always after running alpha, it is true that always after running beta, we're safe. Now, the most deceptively simple axiom in the entire world, but it's super powerful because once we believe in it, so we have a mathematical soundness proof, it is correct compared to the semantics we just defined a moment ago, all of them are, then every occurrence of a semicolon operator can just be turned into splitting the box. But the most important thing of today is the differential equation, and sure, one thing you can do with a differential equation is to show that if always after an ODE, or if we want to prove that always after an ordinary differential equation system P is true, then if we know the solution of the ODE, we can instead say for all times, if you plug the time into the solution, do the discrete assignment, then P is true and the two are equivalent. That sure is correct, but the problem is, of course, that has a lot of side conditions, so it's violating the uniform substitution principle. Like this has to be a solution and the solution of the symbolic initial value problem, not the numerical initial value problem. And of course, it only works if the ODE actually has a solution, and moreover, only works if it has a solution that you can write down, and moreover, only works if you have a solution that you can write down and later on reason about the quantified arithmetic of it. In other words, this had better just be polynomials or rational functions or something like that, because otherwise, Tarski's beautiful result of quantitative elimination being possible in nonlinear real arithmetic no longer applies to this. So even very simple differential equations will no longer be possible to reason about with this naive thing. So there in fact is a soundness and completeness principle here. So first of all, everything I tell you is sound, but it's also complete relative to either differential equations or relative to discrete dynamics. In other words, you can answer questions about hybrid systems exactly as good as you can answer questions about differential equations, or exactly as good as you can answer questions about discrete systems. Sure. If you don't understand the differential equations, you can't expect to understand the hybrid system that's around it. Right? But shockingly, if you only understand the differential equations well enough, all the discrete thing will be possible to prove. There's actually, this is constructive theorem, so you can reduce all questions about hybrid systems to just differential equation questions. with a recipe. It's a long and complicated recipe, but you can do it. And shockingly also the other way around. You can also reduce every question about a hybrid system with what I've shown you to a question about discrete dynamical systems instead. And as long as you're just able to answer either of the two sides, you're done. So these are the two.
When you define a discrete system, do you have a parameter? Let's say, for example, on time. What is the size of the discrete time?
Yes, good question. You will have ultimately that's one way of this reduction will use Euler, explicit Euler axiomatization basically. So one of those will have a certain step size that you follow, and it's of course very important you get the step size correct. So you can't expect to say, oh, I choose my favorite step size and then hope that I've described my continuous system well. That of course doesn't work. You need to make sure that it works for all sufficiently fine step sizes and so on. But that's the way how you can ultimately get the discrete into continuous exactly in agreement and reduce all of hybridness around it to just exactly one question. And that's also our justification today why it is okay to simply only zoom into the differential equations, even if they're already interesting for their own sake, obviously. But I'm not making a mistake by projecting everything that I say from now on to just the differential equations question, even if part of the motivation is to study hybrid systems. But there's a bunch of papers you can look into for these completeness theorems. So here are the corresponding axioms that we have for differential equations. I'm not going to go through them like this, but instead show you in pictures first what they do. The one is the differential invariant principle. So if this is the plot of the vector field of the system, and this is the global solution, and we want to make sure we never enter the bad blue region, then one naive way of doing it would be start the system at each of those points, infinitely many, compute solutions at each of those points, and check at each of the intermediate points in time, infinitely many, whether we ever get into the bad blue region. If you have that much patience, you have a proof, but I don't. So instead, the way we do this is much more easily by just looking at the vector field himself, like Henri Poincaré told us to, right? So look at the vector field, and if the vector field ever points from safe to unsafe, I guess if the system could follow that, we would be in trouble. And if it never does that, then the intuition is, if we start safe, going to point from safe to safe, safe to safe, safe to safe. So we have to be.
But the vector fields are very local.
Yes, they're super local, right?
Right.
Yes, that's an absolutely
so
local
even
principle.
if it points to the bad, then
Yeah.
it doesn't mean that it will go there.
Yes, precisely. That's sort of the thing. It's completely local reasoning principle, and the thing is you need to make sure that you do this in a sound way. And having done that, you don't expect this to be sufficient, right? In the sense of that alone is the only reasoning principle cannot possibly be enough, right? You need a little bit more than that. Yes, precisely. That's this differential invariant principle. That's the first thing we will adopt, and I'll show you the proof rule in a second. Another logical reasoning principle is cut, that we generalize to differential equations like so. If we have a proof that we cannot enter the red region, then I can cut it out of the state space. Having done that, we will then find out, oh, now that I know that I cannot go down there, I will also find a proof why I cannot go up into this other red region, cut it out of the state space. Having done so, I look at the result and say, no wonder the system is safe, I ran out of bad blue regions. Good. This is useful, for example, I think my favorite example is if you have a robot and you don't know what the robot does. If you first prove that it cannot fly, you can restrict the analysis to the surface of the Earth. If you then prove that now that it's on the Earth, it cannot leave the road, you can restrict the analysis to the road, and then the lane, and then make sure you don't bump into the car in front of you. Each of those successive steps are kind of useful. But of course, you can't assume ahead of time that apparently it never leaves the road. You need to first prove it. That's precisely the differential calculus.
I'll give you another example when you play Sudoku.
Oh, how so?
Because you eliminate some things that could be.
That's true.
That's how you eventually identify what is.
That's true. I hadn't thought of that.
Okay.
Differential ghosts, and here they come, right? So maybe the most shocking proof principle. But what sometimes happens is that you have a differential equation you just cannot analyze. And then the strange trick is we can make it more complicated by adding in a new differential equation that wasn't there before. And all of a sudden understand the relationship between the two. So the relationship between these two will all of a sudden be a beautiful energy invariant, for example. And this is really the proof counterpart of dark matter in the sense that also physicists looked at the universe and said somehow that's strange. My invariants don't balance out. It shouldn't be like that. Let me dream up something, hypothesize that it evolves like I please, And then all of a sudden I find that this generalized energy invariant of the universe again works out beautifully. We do the exact same trick for differential equations.
Does that actually mean the system that you're given with is underdetermined?
Not necessarily, but what often happens is that, hold on, let me say that differently. What sometimes happens, and exactly in this case, for example, the system is very determined, but it's a weird one, it's losing energy, as you see from the picture. That shouldn't happen because you won't find energy invariant in a system that's losing energy. So you make up something that accounts for all the energy that apparently is lost in friction in the system and say, oh, it balances out again, great.
So it's not closed.
Precisely, right? That's often one source of this,
But not closed.
but not the only source. And we'll see in the rest of the construction why, even if that's the canonical place to look for, in other circumstances, these principles are also super useful. Good, enough pictures. Here's the proof rule. Differential invariant proof rule just says that if I am in P in the beginning, and I want to show that I am in P still, when I follow a differential equation, x prime equals f of x, within the evolution domain constrained region Q, so some first order arithmetic that tells me, this system cannot leave Q by definition. Why is that important? Because there's a hybrid system around it, and whenever you run out of Q, you're supposed to do something else and do something discrete, for example. So, and then it is enough to prove that your evolution domain constraint implies P prime, so think of this as kind of sort of a Lie derivative of P or something like that, even if this is the formula. So a Lie derivative of P, which actually we define as a differential computation of that, but in a way where you leave a discrete shadow of the differential equation around. So you say sort of naively that, well, if x prime equals f of x, I guess I know that x prime has the value f of x now. That's kind of the least I can read off from a differential equation. And so what this is doing overall is just looking at Lie derivatives. Or intuition. Dynamics pushes us to where P is becoming more true, which is sort of what this says, right? Then I guess if it was true in the beginning, it's true again. Right? Very simple local reason.
So which part is called invariant?
And P is an invariant if we have a proof of this, but it's a differential invariant if we can prove it exclusively by this proof rule.
Okay.
Right? So P prime, forgot if I have an example, but P prime is just take the derivatives everywhere, basically.
So P is the differential invariant.
Yes, precisely. Right. P is then the differential invariant. Here's another proof principle. It does not only apply to invariant questions like here, but it's enough to understand it.
Because I'm ignorant about the logic.
Please go ahead.
What does the fraction bar mean here?
Which thing? This thing?
No, yeah, the fraction. It looks like a fraction, right?
Oh, that's a syntactic turnstile. That just means.
Yeah, that's why I like to understand.
Yes, thank you. That just means the conjunction of all the formulas on the left-hand side imply the disjunction of all the formulas on the right-hand side.
No, it's fraction. The line, the horizontal.
Oh, that one! I found it. I'm sorry. Yes, I didn't see. For me, this stops being a fraction. This is a proof rule. What I mean by that is, yes, I makes sense. This is a proof rule, meaning if we have a proof of this, then we have a proof of that by this differential invariant proof.
If we have the proof of the top. then
Precisely.
we have the proof of the
So the way we operate is following Gerhard Gensen's sequent calculus principle. We ask the question at the bottom, so we start with our favorite desired conclusion, and then we work backwards toward the top, toward the top, toward the top. And when we're done with that, we say, wait, it's sound if the validity of the formula on the top implies the validity of the formula in the bottom, and then we keep on going downward and say, because that has a proof, so that has a proof, so that has a proof, so that has a proof, if all the proof rules were sound. And so my favorite conclusion at the end is.
So why do you use imply?
Because implication already has another meaning for us. Implies already means the thing it always does. If the left-hand side is true, then the right-hand side is true. But that's not enough, because this here doesn't just mean we want this implication to be true. It means we want this to have a proof. So we want this to be a valid formula, meaning true in all states, as opposed to just true in the current state. Good question.
Thank you very much.
Yeah. This is now Gerhard Gensen's cut principle, just for differential equations. So if you have a question about an ODE, you can prove another question about an ODE, prove that you never leave C, and after you've done that, you can change your dynamics around and edit C into the evolution domain constraint. Usually, of course, this is a very dangerous operation, because if somebody says, I would like you to show this, and you say, I've proved something about another system, they would say, great, but what about mine? Yeah? Here, of course, you first prove that he can't leave C, and then assume that he cannot leave C. So it's a pseudo-restriction, actually, which makes that fine. Very simple proof principle as well. Okay? So, or, if you prove that we can never leave the blue region, if we stay inside the green region, then from now on, of course, we can assume that we stay in this intersection of the blue and the green region, such as that.
What is the it's called priority? I mean, you didn't use parentheses.
Yes. If you look at the syntax, the parentheses have to go like this, because there's always one logical formula which could involve an and attached to a differential equation. Right? Okay? And then the last proof principle is differential ghosts. If we settle on proving an invariant question, we can dream up a new differential equation, y prime equals g of xy if we want to. And then if p is equivalent to g for some y, then because we have a p, because they're equivalent, we also have g for some y that we don't know anything about, then y changes, right, along this differential equation system. But if g is still true at the end, then we don't know what y, but we never wanted to know. So because it's still true for some y, it will imply the p that you want at the end. So that's the differential ghost principle. And you can show that these are not just some stupid principles, but also that they strictly increase the deductive power of the system. So there are questions that only differential cuts can prove, that differential invariants cannot prove. And there are then questions that only differential ghosts can prove that the other two together cannot prove. So each of them actually adds something into the proof system. Do you all believe these reasoning principles? Because otherwise I would have to stop here and we should discuss about soundness of these things before I talk anything completeness.
In these things, in the last one, small g, who provides it? So
you do, as you're doing the proof. And I will be doing that as I'm doing the rest of the proof today because I'm arguing for completeness of it, right? But the principle for these things is I'm using them bottom to top. So here the question is, wait, who's got the C, right?
Yeah.
If you know the C, you can do a beautiful differential cut, but you still need to find the C that helps you in your proof, right? Here, likewise, if you know the ghost and maybe the rewritten pre and post conditions, then you can just use the rule, but the question is, where do they come from? And can you always find such things if it's true? Right? So that's precisely the question of today. It actually turns out you shouldn't have believed these because they're actually not sound. Because, and for a subtle reason, the problem is in the differential ghosts. What would not help us is if we reduce the analysis of some differential equation to the analysis of another differential equation that explodes in finite time. Right? That explodes in finite time. Because if you say you want me to verify your self-driving car, and I say, sure, I can parallel compose your evolution with something that blows up the universe after half a split second. And until then, you were really safe. That isn't good enough, right? So the point is, you also need to make sure that the differential equation, the new one you're adding into the system, at least has, well, either a global solution, that's a bit of a strong requirement, but at least it should exist for as long as the old one did. And the best, easiest way of making that happen is just to say that your ODE should be linear in the new variables and can have arbitrary stupid degrees in the old variables. Good. So all of these, I need to be very careful about the soundness of these things, because otherwise it doesn't help if I can prove everything out of it. Good. But now let's switch gears into trying to prove a lot of stuff out of it and trying to understand, wait, where do the cuts come from? Where do the ghosts come from? Why and how do we do this? And interestingly, so the cool theorems are that what you've seen is sound incomplete for algebraic invariants. So every algebraic variety that is a invariant of an ordinary differential equation system of polynomial right-hand side, okay? If it's true that it's an invariant, then there is a proof that it is an invariant from the three reasoning principles essentially you saw, and this even decides whether it's the case. So you just run the thingies and it will tell you yes if and only if it's true, and it will tell you no exactly otherwise.
And is it quick?
Shockingly quick. But of course you can always write down a 20 million dimensional differential equation in which it will take longer than you want it to take. We haven't gone for optimization yet in there, and I'm sure there's a lot of optimizations. And also, If you add one reasoning principle, essentially, then you get that is also true for every real arithmetic formula. So every semi-algebraic set that is an invariant for the differential equation system, also this thing will prove it. Polynomial is what, we assume that because it's very, very, very helpful, but it's not like it's really limited to polynomial. It can be a little bit more, because you can, for example, if you have a sine or cosine function in there, you can introduce new variables and then they're gone again. So just keep that in mind. Good. So the first step that we're doing is to worry about Dabou polynomials. So these are the ones that, at least on the evolution domain constraint, satisfy that the lead derivative of the polynomial with respect to this ODE is a polynomial multiple of the polynomial itself. Originally, Gaston Dabou did this in 1878, and we can now derive this reasoning principle. So it is a correct reasoning principle, but we do not need to believe in it because it just follows from the rest. And I'll show you how.
Excuse me.
Yes.
In all these presentation here, when you use x prime, is x a vector or?
Yes. X prime equals f of x is a vectorial differential equation system of polynomial right hand
And so
side.
is all the other. By p prime?
P is not yet vectorial.
Right.
I will get to when P is vectorial in 2 or 3 slides. But x prime equals f of x is just actually a vectorial differential equation system. Yes, precisely, right.
P will be scalar.
And P is an ordinary polynomial of these 15 variables or something like that. So it's a multivariate polynomial in the variables of the, so here. So x is a vector and g is an ordinary polynomial, not a vectorial polynomial in these systems. Because otherwise this wouldn't type check. Okay. Good, let's prove this. And here's an example of a system, for example, where every point inside the circle will converge to the zero equilibrium point. Every point outside will go away, and the circle itself is stable. And here's sort of the outer is a limit cycle. And here's sort of the opposite. Oh, hold on, that's actually the same picture. I thought I had the opposite on there too, but apparently not. Here's an example of a differential equation system for this polynomial right hand side, and this is an invariant, and indeed this circle is an invariant. So p equals 0 is true at the end if it's true before. I didn't have space to write this down. And you can indeed find a cofactor g such that the lead derivative of the polynomial is a multiple of the polynomial with some polynomial cofactor. And how we derive this proof principle out of the ones we already saw is by using differential ghosts with a counterweight, y prime equals minus gy. So this thing has p prime equals gp. And the most naive thing to do would be to say, maybe let's introduce a shadow variable that plays the role of p. But then the problem is, how do you relate this shadow variable to the evolution of p itself? So the trick to make that work regardless is you introduce a counterweight, so a new variable y, such that y prime is minus gy. Notice that is linear, so it actually exists for as long as x itself exists. And then the question whether p is 0 reduces to proving that py is 0 while y is not 0. Because that clearly implies this, right? Good. Having done so, you introduce yet another differential ghost for a counterweight. So something that counterweights this one. So you introduce a z prime equals gz, because y not equals 0 then reduces to proving that yz is 1, because if yz is 1, clearly y cannot have been 0, and that then implies that clearly py being 0 must have implied that p equals 0. And in addition, these two differential ghosts and counter differential ghosts are exactly such that py equals 0 and yz equals 0 are now trivial differential invariants just by construction of the whole thing. So here is this in slightly more generality. What if you have a Dabou inequality? So instead of an equation, you have that the lead derivative of p is greater or equal to gp, and you're interested in proving either that p strictly greater than 0 is an invariant, or that p greater or equal to 0 is an invariant. Both of them follow from just showing that the lead derivative is greater or equal a Dabou multiple of the polynomial itself. But again, so this is basically Grönwald's principle in disguise or something like this. But you don't have to believe this as a proof rule either, because it already follows. So here's a similar system as before, just with an additional plus x cofactor to make sure that it's not a trivial inequality, it is actual really an inequality that now happens. This is how the system looks like. And indeed, the thing out there is now an invariant because, well, inspect the vector filter carefully or just do this proof.
I have
Yes.
a couple of questions. So this particular system, is this an academic example or
I made this up, this has no meaning. Right.
And second question, so here P was specified.
Yes, because P is always specified, because here it is part of the question. In the bigger scheme around it, of course, we will somehow have to make sure, so let me step back. P is specified, right, but G is not. So G you need to creatively dream up in the process. And we will ultimately, for completeness, have to make sure we will also find all of those G's to make sure that your original question can be answered. Okay? The proof idea why this is a derived reasoning principle, it already follows from the things we have, is very similar. Again, differential goes to counterweight y prime equals minus gy, so the opposite of that, right? Because then p greater than 0, respectively p greater or equal to 0 reduces to py greater or equal to 0 and y positive, right? And then again, you need something to show you that the new y is positive. For this, again, you need the counterweight. This time it's a bit different because the question is a bit of a different one, because you need y to be positive, but by introducing a differential goes for a counterweight, z prime equals g over 2z, then y being positive reduces to showing that yz squared is 1. And then the things are so constructed that precisely those two are trivial differential invariants. You just, for example, take py prime, and that's of course p prime y minus gyp because y prime is minus gy, right? But then because p prime is at least gp, this whole thing has to be greater or equal to 0. So they're sort of made true by construction. And of course, because y is positive, the entire thing will be greater or equal to 0. Okay? Here's another example like this. Here's another example like this with a 3-dimensional differential equation, and x greater or equal to 0 happens to be an invariant of this set. Then the idea how this works is that, for example, here's one point where x started greater or equal to 0 in the beginning of time, and yes, it stays greater or equal to 0, but notice it almost drops below 0. For the reason that it almost drops below 0, the simple differential invariant principle, which works by Lie derivatives, cannot work on this example, because it would basically argue that, wait, if it's always going up, then I guess we're obviously safe, but it's not always going up, it is also going down again. And in fact, it almost shoots below 0, right? It's quote unquote a bit of a miracle that it stays just a little bit above 0. So that's why differential invariance alone cannot prove this. But this derived proof principle, Darboux inequalities that essentially follow from differential ghosts, can prove this regardless, because intuition, what they would do is introduce this counterweight, right? Y prime equals minus the cofactor y, such that x greater or equal to 0 now reduces to xy greater or equal to 0, because you know that t is greater or equal to 0. And then the question is, wait, this one, how do I know that this is being controlled? And you introduce the counterweight, you introduce a z prime equals minus g over 2z, such that the question whether y is positive reduces to proving that yz squared is 1 and yz squared is 1. And notice here again, this looks like the system is exploding in finite time, so it looks very dangerous, because it would truncate the analysis beyond the point of existence, basically, of the solution of the differential equation. But it doesn't really, because there's the counterweight, the green thing that is in a good relationship with the blue one, such that yz squared is 1. So in other words, the blue y curve cannot have actually literally exploded in finite time. It must exist at least as long as x existed. So it was a sound reasoning step to do the entire thing. And of course, because these differential equations are linear in the new variable, that has to be like that. Here's the derivation in a little bit more detail. I'm giving you merely the idea, but this is what would happen if you really took the axioms and did the proof. You have your original question, you introduce with the differential ghost principle a new differential equation, You change the post condition around conservatively because sure, if you know that y is positive and py is greater or equal 0, you can prove that p is greater or equal 0, or greater than no matter what you would need it. And then you do a differential cut to prove that y is positive because you need that in the rest of the analysis, but y obviously is positive because the Darboux principle we already saw proved that y prime equals minus gy will stay positive if it started positive. And then up here you do direct differential invariance on this, basically the thing I had on the slides already. P prime y minus gy p is greater than 0. Then you show this and then assume this by the ordinary logical cut from Gensen. And likewise, then you do the second ghost, you introduce the green ghost. So that's how these proofs look in a little bit more detail. But it's not the level of detail that I wanted to pursue for this talk. Good.
But these proofs are produced by computer?
No, by us. But in our tactics, this is precisely what the proofs will do. So our Chimera X-theory improver will produce these proofs under the hood, so that if you type your question, it will do these proofs to make sure that you don't have to do them, but it will just come back with a, yes, I found the proof. Here it is. But, good. Now the vectorial case. So Darboux polynomials also work for the vectorial case. If P is a vector of polynomials, and the whole vector of polynomials is 0 in the beginning, then it's 0 all the time when you follow the differential equation. And vectorial Darbouxs are also a derived reasoning principle. They follow from vectorial differential ghosts. In this case, the lead derivative of the vector of polynomials is now a multiple of the vector of polynomials, but now, of course, a matrix polynomial multiple of the the single polynomial isn't good enough anymore because it doesn't type check. But if the lead derivative of the vector of polynomials p is a matrix polynomial multiple of the vector of polynomials p, then also p equals 0 is an invariant of the system. And that, again, is not a reasoning principle you need to believe in because we just derive it out of the primitives we already had. The idea is kind of similar to the ones we had, but there's a twist in it. Do you happen to see the twist?
Like it's not non-commutative, I think.
Yeah, right.
And I think you should, in the formulas before, you did some writings by the commutation. So the counterweight should be like transposed or.
Precisely, that kind of thing will definitely happen, but more so for important reasons. The proof before said, let me introduce a counterweight and make p equals 0 follow from py equals 0, but y is not 0. That isn't good enough anymore. Because if p is a vector of polynomials, even if it multiplies with y, that just means they're orthogonal. That doesn't mean anything about p itself being 0. So the tricky bit is that you introduce a counterweight y prime equals minus gy, so that instead of p equals 0, you prove that py equals 0. This is not scalar product. But py being 0 doesn't imply anything about p being 0. It's just not good enough, even if you know something about y. But then the point is, you just do that again. You do introduce yet another differential ghost, right? Yes. Lots and lots and lots of them until you have y prime equals minus yg as a whole zoo of differential ghosts, all of which satisfy yp equals 0. And then if you choose your y cleverly, of course that implies the p is 0. So you need to choose a y to make sure that its determinant isn't 0, which implies that it's not a singular matrix. And in other words, p actually is 0, and you can prove that just by in arithmetic. And then, of course, you just need to prove that the determinant of y stays non-zero if it started non-zero. But that's yet another Darboux use, basically by the Abel-Ubil principle. So that the determinant of y and its lead derivative is minus the trace of the cofactor matrix times the determinant of y. And so that also, this is a polynomial cofactor, even if a bit more complicated one. In other words, this is already provable by the Darboux principle we saw. I know you did right. What this is doing intuitively is now a continuous change of basis. So what this is doing is now, other than before, where like differential ghosts were used to like do something against the deficiencies in systems, right? They were systems that were leaking energy or systems that were gaining energy, so they were not actually closed systems. And you added the differential ghosts in to make up for that, right? All of a sudden here we're using differential ghosts in another way. Even if the original system was perfect, right, a closed system describing everything, we still use these new differential ghosts to add new variables into the system that are merely there to make the analysis easier. And that's where the name ghost comes from, by the way. These are ghosts because they're not part of the original system. They're made up just for the sake of making our analysis easier. And they co-evolve in ways that fit us, ways that make our analysis good. And so what you can think of this proof here as the system undergoing a continuous change of basis in a way that is cleverly defined to make sure that the thing you originally cared about, p equals 0, is an obvious constant of the new system. So one way of seeing that is basically here's some dynamics and so on, and it changes in crazy ways and so on. But if you make a clever change of basis in a continuously evolving way, so your change of the basis you're looking in keeps changing as time progresses, then if you do this in a clever way, the point that really was evolving, all of a sudden it has constant coordinates along this morphing coordinate system all of a sudden. Now the question is, why is it okay to morph coordinate systems like that? Why couldn't that cause unsoundness? But because everything was just a bunch of differential ghosts, which we already understood as sound, the entire production must have been sound. There could have been nothing that was wrong in the process. So it's okay to do these continuous coordinate changes. Good. In fact, the next thing, well, this one, hold on. The next thing we're going to move into is this was all kinds of equality reasoning, but only for where the lead derivatives is a polynomial multiple of the polynomial or a vectorial multiple. So, but that's not always enough because sometimes you will have to look at higher lead derivatives to determine what's really happening. For example, here's an example where the first lead derivative at this point is 0, the second lead derivative at this point is 0, and the third lead derivative turns out to be negative, so you move inside the set. And you somehow need to emulate this in reasoning as well. So you move on from vectorial Darboux, which are derivable, to what are called differential radical invariants. The name comes from precisely like radical ideals, right? The thing where higher powers are contained in the lower powers, or the ideal generated by. Here's the same thing just for lead derivatives instead of for powers of polynomials. So what that means is p equals 0. If you have a bunch of assumptions, p is equal 0 is true after a differential equation. If all the lead derivatives, so if p, this particular blue parentheses thingy means the ith lead derivative. If in the current state and under the current evolution domain constraint, if all the lead derivatives are 0 up to n, and the nth lead derivative, so the next one is in the ideal generated by the previous lead derivatives or against a polynomial multiple of these, then you do know that p equals 0 itself is going to be an invariant of the system. And in fact, so this is like the Darboux principle, but generalized to higher degrees, basically, right? If you had n equals 1 here, then it would just mean first lead derivative is a function of p0, right? And now you say, well, that's okay if just the second lead derivative is a function of the zeroth and the first lead derivative, and so on. And now, how do you argue why differential radical invariants are correct to be used without having to believe in them? They follow from the vectorial Darboux. Because it's just, you set up your matrix such that you take the vector of all the lead derivatives you had so far and put the cofactors and P2 will be, the lead derivative of P1, go figure. Right? So that means that once you have vectorial Darboux established, you also have differential radical invariants derived. So everything you saw so far just follows from these three little reasoning principles I gave you. And moreover, this right-hand side actually has to happen eventually because it's in the Noetherian domain. The polynomials over a field form in the Noetherian domains. In other words, you can't have an infinite ascending chain of ideals. They have to stabilize eventually. In other words, at some point, the 772nd lead derivative will have to be contained in the ideal of the previous one. Well, not literally that one, but at some point it has to happen. Okay.
So where is the radical part here?
Radical, it's in here, right? If you think of the definition of a radical ideal, it's something where the nth power is in the ideal contained. And here, this is not the nth power, this is the nth Lie derivative.
Right.
So it is precisely analog to the radical ideal condition, but for the differential version of it. So it's the nth Lie derivative that is contained in the ideal generated by the lower Lie derivatives. Let me, if you think of the definition of the radical ideal, right, it's all the polynomials such that some power of the polynomials is generated by the powers, right? Where p are in I of, hold on, yeah, well, that, right? Here we don't do powers, but we take this, which means I is the Lie derivative of, hold on, easier. This way around, pi plus 1 is the Lie derivative of pi with the vector field, where, of course, and the zeroth Lie derivative had better be the polynomial itself. So it's analogous to that, right? It's precisely yes, it's not the exact same thing, but it's precisely analogous to that. It's just the Lie derivative counterpart of what you would do.
But this seems just to say that P satisfies a linear differential equation of order capital N, and you're using the companion matrix here, right?
I haven't thought of it that way around. Yeah, but you're right. Yeah. In fact, this is also, by the way, these kinds of things are also how we're generating the P's. This proof rule now is not just a sound proof rule, but it's a sound and complete proof rule. This proof rule not just establishes that P equals 0 is an invariant, but the proof rule applies if and only if P equals 0 is an invariant of the system.
You didn't claim that.
I didn't claim that yet.
What's that gamma? Is that a gamma?
Yes, that's just the set of all assumptions you have. It can be any formulas, any algebraic.
Including P equals 0.
Yes, precisely.
You can also, if you switch to the dual space, you can view this geometrically, that you're looking for a cyclic vector.
Right.
Okay.
Yeah.
There are algorithms for doing that.
Interesting.
Yeah.
We should talk. Great. So how we do this is that once we have this proof rule differential radical invariance, we also have a proof that these are complete, meaning that P equals 0 is an invariant of the polynomial differential equation if and only if this proof rule says so. And all of a sudden we can twist it on its head and say, now find me the set of P's for which that is an invariant of the differential equation. Next step, so this is basically the end of the equality case, because every algebraic variety in the reals can of course be reduced to a single polynomial equation. And so every algebraic variety, if it's an invariant for the polynomial differential equation system, this proof rule will tell you so. And this proof rule did follow from the three primitives I gave you: differential invariance, differential cuts, and most crucially, differential ghosts. So blowing up the dimension until the motion of this thing gets simple.
So in the differential radical invariant, you want the initial condition to be all 0?
No, not necessarily, but you know something about the system initially, and as long as the something that you know about the system at the initial point implies that at this particular point all the Lie derivatives vanish up to the rank.
Those are Lie derivatives, not just the
Right. If at this point think of this as any algebraic variety or any semi-algebraic set. If at this, characterizing your initial condition, at your initial condition, if all the Lie derivatives vanish, then P equals 0 has to be an invariant at that point.
You mentioned some time ago that think about linear equation. You don't mean linear because fx is not linear.
No, it is not linear. It's for non-linear.
Quasi-linear
Yes.
dynamics.
F of x is any vector of polynomials with the same dimension that x is, of course, right?
But the x prime, so it is quasi-linear in some sense because you can isolate x prime, so you don't have to worry about separate and things like that.
I'm not sure I understand.
So if I give you a first order nonlinear equation, I might have a derivative. I might have some x that multiplied by x prime.
Yeah.
So would you have to separate out, say x is not 0 before you right? X prime equals to.
Not here, but that's the thing that we have to do in a minute, right? So for algebraic invariants, or for algebraic varieties of invariants, that's just completely enough what I told you. But as soon as we go to semi-algebraic sets, for example, p greater than 0, all of a sudden, these things is what we have to do. All of a sudden, what we have to do precisely is this, that, for example, p greater than 0 is an invariant of our differential equation. Notice I left off the evolution domain constraint now because it's going to get annoying otherwise. It's true also, look at the paper, but it just doesn't fit on the slides anymore. Then it's an invariant if we're at 0, the first Lie derivative is greater than 0, and if the first 0, then the first Lie derivative is greater than 0, and and all the way up to the differential rank, where if all of the previous Lie derivatives are 0, then the next one is greater than 0. That is then enough to imply this, and it also does follow from what I showed.
Why do you put commas in those phrases?
Because it's not what logicians do. So what they do is
Okay.
yes, but yes, fair enough. So that precisely does this thingy here, right? Where we say if we are at a point where, let's see if the first Lie derivative points inside. If it doesn't, because it's still 0, but certainly not pointing outside, then let's check if the second Lie derivative is blah, 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 blah. And until we find one, the most significant Lie derivative, whose sign tells us what's happening in the system. And again, of course, remember that this condition eventually ultimately actually happens by Newton's theorem. So this is what happens if we have an arbitrary semi-algebraic set as an invariant. So P is a semi-algebraic set, or a formula over first order real arithmetic, because they're equivalent. And in that case, the proof rule says that if we spell out P in this normal form with some equations and strict inequalities, and if you also spell out not P with some equations and strict inequalities, then that thing up there, which is defined down there, is the thing we need to do. I don't know how you feel about this proof rule. I feel about it in very horrible ways, because if somebody would tell me, this is what you need to believe in right now for proofs about differential equations, I would say, no way, are you kidding? I don't want to believe that. So the point is, you don't have to believe this particular thingy because it's just derived out of the things we saw. And that's super important because we bake in just very small atoms of reasoning. Those you scrutinize the hell out of them and make sure they're really, really rigorously sound. And the rest is just, mechanics in a computer that staples us together. If we ever get this implementation wrong, no biggie, because you just won't prove the system you want to verify. And most people notice if they can't prove the thing that they want to prove. Nobody notices if they can prove the thing that they shouldn't be proving, right? So that's the way how it is very important that we have an extremely tiny Sameness critical core in our system. In fact, only 1,700 lines of code that are Sameness critical. Everything else is not. It's very important. The rest is just built on top of it. It's important to me that our proofs for this are correct, but if we mess this up in a computer, no harm done. Good, but in order to show you a little bit more about... Yes?
You still have to write the code to derive these complicated, more complicated rules.
But it's only 1,700 lines of code that matter. Our system is designed by uniform substitution. It's Church's uniform substitution in very clever ways to make sure that the things that are on the soundest critical path of the system is minuscule. It's just a very basic...
No, I understand that. So the core is fine.
Precisely. Around it, we still need to do the code that precisely does the derivations I just showed you. And we've done that, but the point is, if this ever makes a mistake, it just won't find the proof. So people will notice and say, wait, I expected to be able to prove this. It didn't prove.
So when you see the proof, you don't see the upper, you only see the core version?
No, you don't only see the core. You see,
you see the upper.
Yeah.
So you believe the upper ones, even if sometimes they may be wrong.
No, because the way our system is designed is it can only give you back, I've proved this fact, if this fact ran through the core. So the thing you see at the end is you see a higher level presentation of this, but the answer, yes, this statement is now a theorem because it has a proof. That only can be printed if our core at some point would happy. That's the way we do this, to make sure that no mistake can happen in this reasoning. a lot of thought went into trying to precisely make sure that you're not misled by some higher level thinking in a way they say, that's good, I think I see the intuition, when really the reasoning on the bottom didn't actually also work out. Good. How we do this is all of a sudden, however, so remember, for algebraic varieties that are invariant, the three principles that I showed you were enough: differential invariance, differential cuts, differential ghosts. With differential ghosts used quite a bit. For the semi-algebraic case, because semi-algebraic sets are annoying, we need a little bit more. What we do need, this is not the actual presentation of it, this is one level higher up, but I think it's easier to understand the intuition of it. One of the things we need is an axiom that implies, or essentially equivalent to the real induction principle, so that P is an invariant of a differential equation. Notice no evolution domain constraint. If whenever I am within P, I can make a little progress locally. In other words, there's some non-negative duration such that I still stay in P. And negative also, that whenever I'm not in P, I can make some backwards ODE progress within not P. So in other words, that means if we move, and this is a part where the semi-algebraic set is an open boundary, then wherever we are, we can still make a little bit more progress, right, within P. We're not talking about the global property, just locally. Right? And, for example, if we are a part where our semi-algebraic set has a closed boundary, then wherever we move, this is still in P, but if we move a little bit too far, such that not P is true, in the backwards differential equation, we can still stay in not P for a non-negative amount of time. That means, like, P doesn't just stop going forward, but also not P doesn't just come out of nowhere when going backwards, right? Whenever not P is true, it was already true for a little while. And the two of them imply that P is in there. In fact, they're even equivalent to that by the real induction principle. This real induction principle is what is underneath this funny thingy here, right? So that's funny, I admit, but it derives from the things you saw plus the real induction principle. And then this real induction principle reduces invariance to local progress properties. These are now these diamonds I can make a little bit of progress toward. And these local progress properties we can prove from just two axioms that internalize the existence and uniqueness of solutions of differential equations. Like so. If a polynomial is still positive, then you can locally follow where it is still positive along an ODE. Obvious, because the polynomial is continuous and the solution of the differential equation is the open set, right? So you know, wherever you are, maybe you leave it in the long term, but not right now, right? That's what this just directly says. There is a solution and it's a continuous function.
What's the little circle mean?
That just means you have local progress. That's easily definable out of the things I showed you. That just says there is a non-zero amount of time that you can follow forward.
Oh, okay.
It's easily definable. Unique solutions is this axiom. So this is internalizing existence, and this is internalizing uniqueness. That says if within Q1 I can go to P1, and within Q2 I can go to P2, then within the two of them, I can go to either of them. So picture, if within the green region, I can go to P1, and within the blue region, I can go to P2, then in fact, without having left either of the two regions, I can go to whoever happens first. In other words, this picture doesn't actually happen, right? Because of uniqueness of solutions. We don't know which one will happen first, but one of them will, and until then, we were in both evolution domain constraints. Right? So this one we use to so the local thingy we now reduce to those two. Whenever we're inside an open set, then we have local progress inside the open set. And whenever we're in boundaries, well, we need all the Lie derivative reasoning that you saw on the previous slide. And we staple it all together by, you know, using uniqueness of solutions in clever ways. With these things, it's basic primitives, you can now derive stuff again. You can again, for free, get to know that you can make local progress within, step back. Here we already know that we can make local progress within P greater than 0, sure thing, right? But within an equation, we can also make local progress if all the Lie derivatives are 0, right? In fact, this is precisely the condition that implies that P equals 0 is an invariant. And if something is an invariant, then we can make local progress within it because there is no interesting evolution domain constraint that will stop local progress. here, we can make local progress within p greater or equals q. If either p is already positive, well, then the continuous principle says we can make local progress in it. Or it's sadly in the boundary, but we can make local progress within its Lie derivative. So p prime is greater than q prime. And that's by using this from right to left, step by step by step by step, we have an induction principle basically, because we can say local progress within p greater than q is possible if either the signs already tell us or it's undecisive, but the Lie derivatives tell us. For that one, we can again say, wait a second, does p prime greater than equal q prime, do I have local progress within those? Well, if the signs tell me yes, if it's undecisive, go to the next one. And that's how we induce our way up the stack, basically. And then, you can also derive these things which you need for mixed progress, which are very annoying. For example, that within p equals 0, you can make progress within either p equals 0 or q positive, as long as like the local Lie derivatives for q don't tell you otherwise, basically. But the point is, these are not so important. These are just things that we derive out of the primitives I gave you in order to be able to prove every true property of it.
Why? Two things. What is the asterisk after p prime mean? Does this still mean repeat or something?
Yeah, that's where the intuition comes from. It means, I skipped this a little bit too fast. It means this. So p prime star is sort of repeat Lie derivatives. What I mean by that is just, it is 0 if all the Lie derivatives are 0. Well, all the Lie derivatives up to the rank, up to where the nth Lie derivative is in the linear, is in the ideal. But yeah, it's just shorthand notation. And here, again, the most significant Lie derivative is positive if the function itself or polynomial itself is non-negative, and if we're at the boundary, then the first Lie derivative is non-negative. If all of them are 0, then that one is negative, and so on until at some point there actually is a significant Lie derivative that says all the previous ones were indecisive, but I know what happens. So these are annoying abbreviations out of that, but the point is, again, unfortunately for semi-algebraic sets, awkward things happen, but we don't need to believe in that because we build it all out of axioms, so it's very easy for us to get this all correct.
And why do you write the arrows on the opposite side?
Yeah, logicians. Sorry. Logicians. This is just backwards implication. It precisely means this implies that, and I just sometimes do that in order to indicate what is the thing you want.
Oh, okay.
I just rewrite the formulas to make sure.
Possible ways.
Yeah, it is. I just rewrite the formula such that the thing we want tends to be on the left-hand side. For that, I sometimes need to use the reverse implication notation. Yes. Okay, but the point is, from what I've just shown you, that you do get the completeness for algebraic invariants, right? So every algebraic variety that is an invariant of a polynomial differential equation system has a proof using the principles I showed you, just differential cuts, differential ghosts, differential invariants. Most crucially, the differential ghosts, because they were used the most in order to introduce enough variables within which the question of invariance is a trivial one. It's just a constant. And for semi-algebraic sets, in other words, for every real arithmetic formula, if it is an invariant of the polynomial differential equation system, there also is a proof. Everything is sound and complete, but in that case, we need a little more axioms. Right? In particular, these two axioms we need in order to characterize local progress. That's all we need. They're complete for local progress. Every local progress property that's true can be proved from these, with the differential cuts, differential ghosts, different. And this one we need in order to capture the semi-algebraic set invariants. In fact, here's another way of writing this. Here's another way of summarizing what happened, at least for open evolution domain constraints. For closed ones, something like that works, but it's more annoying. That within the evolution domain constraint Q, P equals 0 is true along a differential equation system, if and only if the evolution domain constraint implies this thingy which said all the Lie derivatives are 0. So this is directly an if and only if characterization, and that of course means we now have sameness and completeness. And it also means if you are given this and you're looking for giving me the set of all P's for which that are invariants, then basically solving this condition is how we can generate invariance for the system. For semi-algebraic sets, well, that was the stupid thingy that mentioned all kinds of significant lead derivatives of P and so on. It was a very annoying condition already without the evolution domain constraint. With the evolution domain constraint, it gets even more annoying because you need to worry about the cases where the direction of motion makes you leave P, but Q is rescuing you because it says you can't go there, or the other way around. Very annoying, right? But it is all derivable out, and so on. You can look that up in the next paper as well. So summarizing, what you've seen is differential dynamic logic exploited in order to prove all true properties of differential equation invariance, where we're completing an interesting step in Henri Poincaré's qualitative analysis of differential equations by giving a logical foundation of differential equations invariant reasoning and a sound and complete axiomatization for it, where for algebraic invariance, all we need is differential invariance, we need lead derivatives, differential cuts, and differential ghosts. But for semi-algebraic invariance, we need a little bit more. We need like logical internalizations of existence and uniqueness principles and the real induction principle, which basically, well, I'm going to get to that in a second. For free, you get other stuff out of that, which I haven't had time to tell you. For example, that you can decide algebraic invariance of differential equations, but also algebraic invariance of algebraic hybrid systems. So if you have an entire hybrid system around it, you can also finish in the blanks of the proof, and it will tell you yes, if and only if the question was actually true for the hybrid system around it. You get local progress properties for EDEs. They're all decidable by proofs. And the thing that I neglected a little bit, but we talked about it briefly, it's actually even more pretty because these are not infinite axiom schemata, which are dangerous to implement, but they're just verbatim copies of the formulas. Plugged in with uniform substitution principles. Very simple Jupiter Church. We've overall seen the impressive power of differential ghosts in action. Let's look at the axioms we've got and see what mathematical theorems they exploit. Because even though I talked about polynomial differential equations, these things are true these axioms hold more often, right? Which is part of the point of this. Right? Identify what this depends on. And differential invariants directly internalize the mean value theorem. They're actually equivalent to that.
What theorem?
The mean value theorem,
Oh, the mean value.
right? They're actually equivalent to that. Differential cuts internalize the prefix closure of differential equation solutions. If you have a solution for 10 minutes, you also have one for 1 minute, right? That also holds that has nothing to do with polynomial differential equation. It holds generally. The differential ghosts, they internalize the Picard-Lindelöf or Cauchy-Lipschitz existence uniqueness theorem for y prime equals a of x times y plus b of x differential equations. And then the real induction principle internalizes the completeness of the real numbers, and then continuous and uniqueness, of course, internalize the existence and uniqueness aspects of Picard, Peano, Picard-Lindelöf, Cauchy-Lipschitz theorems, and so on. The point is, these are true very generically for many classes of differential equations, which means these are also true for many classes of differential equations. It's an interesting question that we're currently after, trying to take this and generalize it to broader classes of differential equations. The thing that can go wrong is that you lose the decidability of the arithmetic that you boil it down to. And that's also the reason why if you start with this differential equation that actually is involving sine and cosine functions, we first introduce new variables whose derivatives are polynomials again, so that because the reasoning is based on the ODE, not the solution, we make our reasoning easier by, again, falling into the Tarski real arithmetic. And the other thing that can go wrong is the rank condition, that at some point you have in the theory domain. So at some point, the higher new derivatives wrap around and you have just a polynomial multiple of the previous lead derivatives.
Do you require constant rank condition all the time?
No, not at all. No. It's also, in fact, you can also look at these things, and because the axioms are so local, you can also reason in local constant rank ways of your ODE in case it helps, or in global rank ways in case that helps, or in mixed ways. It's a very flexible principle, and we don't require, beyond, at the moment, polynomial differential equation systems and arbitrary real arithmetic postconditions, we don't really require anything else. Another way of looking at this talk is, well, these were the axioms we put in, and they're all actually very easy, right? Lie derivative reasoning, differential cut reasoning, differential ghost reasoning, making up new ODEs, real induction principles, then the existence principles, and the uniqueness principles. These are very, very simple atoms of reasoning. And the point is, out of these obviously sound atoms of reasoning, all kinds of much more complicated properties of differential equations can be proved just like that, which is, I think, a very, very interesting development. And part of the point was that we're exploiting these differential ghosts to say, if we don't like the original ODE, we can transform in clever ways that we make up for the sake of the proof to make sure that we like the ODE, for the sake of the analysis of the concrete invariant that we care about. What is not answered yet is the question that even if this says it's all standard complete and always possible and decidable, we do not yet know what is the most efficient way of doing that. Because in some of these cases, we can look at our construction and say, yeah, that always works, we see, but in case you have an open set, there's an easier shortcut, or things like that. That we haven't fully explored yet. But thanks a lot for your attention. In fact, if you're interested in this, there's also a textbook coming up where a lot of the things I say are explained in, and not the completeness things, they're not part of it, but a lot of the like underlying technical development and so on, and the reasoning principles are explained in a way that our undergrads like a lot, for example.
Who did this first? Who did this first? This kind of theory.
Well, differential dynamic logic is what I came up with.
Oh, you came up with it.
Yes, also the differential ghost principles and
How
so
long
on.
ago?
Differential dynamic logic, I think the first paper I wrote on that in 2007 or so, roughly. But then, I mean, that didn't have all the differential ghosts principles yet and so on. So I came up with them, I forgot when, 2010 or so, roughly. So this is like a culmination of a longer term development that you see here. And the first two completeness theorems, I think, are from 2008. And 2012 is when I did the other one. And then the third completeness theorem, the one for zooming into differential equations, that's now new. That just appeared at the Logic and Computer Science.
In the calculation of these differential cuts, so do you use Grobner basis, for example, to get some sort of open set?
Yes. Like what we do is we do use Grobner basis for. In fact, we use it in multiple ways, but the most obvious way is for computing the differential, the rank, right? So when the Lie derivatives wrap around because they're contained in the Lie derivatives in the lower Lie derivatives. That's precisely what we use a Grobner basis computation. But it's not the only part where we also use
You also
Grobner basis.
compute radicals of ideals? Do you compute radicals of differential ideals?
We don't do that. Maybe we should, but that's not what we do. But we do use Grobner basis also for the arithmetic, for the real arithmetic, I should say, at the end.
Okay.
Because in fact, it turns out if you just use Grobner basis, it isn't good enough because you cannot prove a whole lot.
So
The complete of the
cylindrical
Precisely.
decomposition.
So Grobner bases are complete of the complex numbers, but most of the questions are specific to the real numbers, obviously. And then we either use cylindrical algebraic decomposition as it comes from Mathematica and so on, or QPCAT and whatnot. Or we also sometimes use real null standards by Stengler, so that we can, using Grobner basis and semi-definite programming and so on, we can find witnesses that we can at the end of the day check very easily with just a multivariate polynomial division. That have the advantage that a prover core can just do that because it's very, very, very easy.
So do you use Mathematica to implement this?
We also use Mathematica to implement the only part where we use this.
And all that.
Yeah, the only part where we do make use of Mathematica is for the cylindrical algebraic decomposition. We also use other tools alternatively. For example, Z3, or we also used Redlock in the past, or CapCat and so on. But that's indeed the biggest bottleneck in a certain sense for us, because in theory this is decidable, but it's also doubly exponential, so it's not fun, right? And that's sort of where, in a certain sense, in principle, when you look at hybrid systems, the hard questions are the invariant questions. But all of a sudden, because we developed so much technology for this, nowadays it turns out that many of the hard questions are, well, but what if you wrote down the right invariant, but the real arithmetic doesn't prove? So that's indeed one of our pain points.
Now, when you talk about the invariants or differential invariants, it looks like that those are loop invariants.
Yeah. Aha, yes, good point. That's a good point. So first of all, how do I say it? So the differential invariants are the differential equation analog of loop invariants, because in a loop invariant, you also say you could reason about a loop by unfolding the global behavior, but you will never get anywhere if you do that. Just like you could reason about a differential equation by writing down its solution, but you kind of have to be a little bit lucky with the ODE for this to work, right? And just like loop invariants reduce the safety analysis of a loop to, well, if it's loop invariant is true in the beginning, and it does imply my safety condition, and whenever it was true before the loop body is true again after the loop body in the exact same way, and that's how I model the differential invariants. Do those do the same kind of reasoning for differential equations? Just the step notion is a different one, because of course in discrete systems there's a well-defined next step state, in differential equations not so much. So you need to work with the lead derivatives instead, and avoid unsound stuff. The differential cuts actually correspond to, they change the evolution domain constraint. So what they correspond to in loop, in discrete land, is changing the loop guard of the loop condition. If you have a while something loop, this would correspond to the step of, maybe I can change something else, I can write down something else in there. And the differential ghosts, they correspond to dreaming up ghost state or auxiliary state in discrete systems, which at least in parallel programs you sometimes have to.
Adding variables.
Precisely. Adding variables that are ghosts. They're not in the original system, they're just put in for the sake of the analysis. So that's what they correspond
And
to.
in general, they are quite arbitrary.
Yes, precisely. Right. And that was state of the art for us till just now, that it was a matter of creativity where you had to find the right invariants to do differential cut widths and the right clever differential ghosts to reduce the proof complexity. Right? And all of a sudden now we know how to dream them up systematically so that we construct them from the original question, and it will work if and only if the original question was true. So that's the thing that is of course much more useful for using this technology.
So the invariant, or in particular differential invariant, would be quite different from the invariant of moving frames?
Yeah, there would be.
It's just totally different thing.
Yeah, I mean there is some relation, of course, because it's not like, I mean, both of them study, of course, invariance of motion in some way or other, but the criterion is a very different one. This is a very simple. These are optimized, quote unquote, to be very easily checkable by a computer at the end of the day. In fact, it so happens that once you find out the differential invariant, the proof is a complete piece of cake, right? Because it's just formed by lead derivatives. I mean, they even reduce the degree in a certain sense, so they're very easy. Like just local checks. It's the creativity is in coming up with them, and this completeness construction sort of tells you how.
So when you try to find invariant or a card or even ghost, do you ever use an ansatz?
Yes, we do that too, right? That's how we generate, for example, that's how we generate the set of all invariant equations that are true in a differential equation. We write down.
You put a bound on the degree or something?
Precisely. So we fix a monomial template or something like this, and then because we have real arithmetic around it, we can say, does there exist parameter choices A, B, C, D, E, such that blah, 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 blah. That's precisely what we do, and for example, that worked really well in some cases. So for example, we took the differential radical invariant proof rule, turned it on its head because it happens to be complete, and tried that out for the longitudinal flight equations, so for the 6 degree of freedom ODE model for actual aircraft. And it just automatically generated 3 very interesting invariants. In fact, we talked to flight people later on, and they immediately understood one of them. And despite trying for 4 hours, they couldn't completely understand the other two. So it's kind of cool, right? But again, this is good technology, but there's still a lot of questions in how to more cleverly symbolically compute with this, because we also tried to generate in the same way with full flight equations in not just longitudinal but longitudinal lateral, and yeah, it always got close to generating some things of invariance, but it never actually terminated with interesting invariance. So I'm sure there's still something we need to do in better ways. But the point is, of course, also that whenever you generate the invariance, this is not a complete recipe for checking each and every one of them. So that's a good development regardless. But it doesn't fully answer the generation question for invariance. That's still the part that can go wrong.
Have you tried the pendulum system?
Yes.
And what happens?
Well, we can prove that, but I don't remember what happens in the invariance for these things.
What I'm asking is that there is a concept of index,
Mm-hmm.
many different versions. Differential index is one of them. And so is that encountered here? It's the kind of number of derivations that you must do in order to get whatever you want.
Mm-hmm. Good question. I don't know.
Because that's, in some, people in differential geometry think that those are complexity issues. Because index 3 would be very difficult.
Yeah.
Pendulum is one of them.
Interesting.
However simple that looks like. But
Interesting. So what happens actually in the differential, what is an interesting observation is that in this differential radical invariant principle, so just form all the higher Lie derivatives and make sure they're all zero, right? The thing that derives from that and is complete for algebraic invariance. What happens in that case is that this differential rank in the sense of how far do you have to go up until all the Lie derivatives wrap around, that in practice is shockingly low. In practice, oftentimes the rank 1 is perfectly sufficient, which means Dabou polynomials are perfectly sufficient. And in fact, you can also look at this. The vectorial Dabou case is only important if you have a higher rank invariant. And you can write them down, you can construct them, but they don't come up in nature that often. So, which is an interesting phenomenon too. Just like in some systems, I mean, there is one. In this one, for example, right? Here, you need to go to higher Lie derivative degrees to even determine what is going on. And I think here and there's two other points where this phenomenon happens, but the majority of the motion of the system compared to these invariants is rather tame, where even a rank 1 computation already tells you exactly what's going on. Which, of course, also means that, maybe it should be possible to exploit this somehow, that the majority of the state space is tame in some sense or other, and just occasionally there's higher rank phenomena that are important in analysis. But these were very interesting questions. So.
I'm just trying to imagine a use case. So, for example, I designed some differential equations, and I have what I expect a safety condition, like some open set. I bring it to you, and your software says that no, you can leave this in principle. Can it also shrink my? So I don't want to extend safety because it will get unsafe. But I'm fine with shrinking it.
I haven't thought of that.
Is it possible to generate shrinking that will be safe?
Well, we do this in parameter synthesis. In fact, one of the original motivations for designing differential dynamic logic was for questions. For example, it's very easy to write down the skeleton of a system and say, I guess if I'm designing a car controller, it can accelerate, it can brake, it can steer left, it can steer right. You just don't know when it's supposed to do that. So in particular, one of the reasons for differential dynamic logic is you can write down those questions about parameters and say, is it true that for every point there is a choice of this parameter such that all the behaviors of the system are safe? In that way, this is sort of shrinking the dynamics of the system until it is even true that the system is safe. But of course, this is sort of more in the mix of it's not necessarily, we haven't done that yet on the evolution domain constraint of the system, for example, to say, you could write it down, but I haven't tried what happens. Say something like, is there a boundary for the system within which the evolution of the system is always safe?
So for example, what I can ask is like, for example, is there an inequality of degree at most 2 such that inside it things are safe?
Yes.
And this will be like a valid formula and it can be approached.
And that means it's decidable whether it's true or not.
So I, using these tools, I can organize this shrinking procedure in some like intelligent way.
Yeah.
So, okay.
Right.
Mhm.
But that there's still like questions remaining in terms of that is the answer in principle, but how you do it most efficiently, that's
Yeah,
still,
sure.
Let me know if when you succeed, because I'm sure there's many interesting questions on that. There's also, for example, some of these computations can be shortcut rather directly by replacing, for example, replacing a Gribner basis computation for has it wrapped around with just let's try the multivariate division and see if that happens to give us the cofactor for the Dabu, because yeah, often that's perfectly sufficient. And so these are some of the things that we are not yet really exploiting as much as we probably should, because there's a lot of shortcuts in the computation that are possible.
Could you explain the universal substitution?
Yes.
Because I think you didn't do that.
I did not.
I think so.
I mean,
I don't remember.
no, I did not talk about it. No.
I mean, we question and you answer, and in the end, what exactly?
Never mind the slides.
Exactly.
So, an eraser. I'll use the other board. Or that eraser.
I think if this right on this side is better.
Good, I will do so. So Church's uniform substitution principle is that if we have a formula, then any uniform substitution instance of it is also true. So if you believe in phi, you should also believe in phi after you substitute formulas in for predicates, terms in for function symbols, programs in for program constant symbols, and so on. For example, can you all see here, or is this a bad spot? Let me know. Okay, so for example, actually, how about this one? This was one of the axioms. A system that has a choice is safe if and only if each of the two branches, all the behaviors of each of the two branches are safe. And because this concrete formula is by bar, I just mean you have the vector of all the variables, not something. Because this is a concrete formula that's in the list of axioms, we've got, I don't know, like 10 or 20 axioms or something like this. This has a proof, it's just copy-paste into the prover core, and then the uniform substitution principle says, oh, but that means if I replace A with a program, let's say x double prime, let's see some different equation, x prime equals
I see what you mean.
V everywhere, and if I put if x greater to 0,
You're careful with the symbol.
precisely, as long as, so the thing that uniform substitution just has to do is watch out to make sure it only checks one condition, essentially, because it's the only symmetrical one, that you're never putting a new free variable into a context where it's already bound.
Right.
That's all it has to make sure. And of course, in the context of a differential equation, you have to keep in mind that the x variable is free in it because it depends on the initial value, it gives the initial value. The x variable is bound afterwards because, well, the value of x changes. And also the variable x prime is bound afterwards because that's the thing I need for the lead derivatives at the end of the day to keep copy the discrete shadow of the x prime variable out. So x is being read, but x and x prime are changing. And then, Church's uniform substitution works beautifully in the
Okay.
Any more questions? Thank the speaker again.